Oh no, I'm so sorry.
Oh, Lyra, it's all right, really. Don't worry.
Okay, so take a look at the sea surface temperature map we've got here. You see that massive glowing red stretch right across the Pacific? That is a colossal patch of unusually warm ocean water. Now, it might seem incredibly distant if you don't happen to live on the coast of South America, but I want to pose a pretty fascinating question to you today. How does this seemingly isolated, microscopic shift in ocean temperature create a massive, chaotic ripple effect that dictates weather, food supplies, and human livelihoods across the entire globe?
Welcome back to The Explainer. I am super thrilled you're here because today we are untangling one of the most powerful and mesmerizing climate phenomena on Earth. We're talking about El Niño. It is just a brilliant example of how deeply interconnected our planet systems truly are. When the ocean breathes, the atmosphere reacts, and every single one of us feels the impact.
All right, let's dive right into this. Here's our roadmap for today. What is El Niño? The physical mechanics behind it. Global weather disruptions, the hit on farms, fish, and food, and finally, the human toll.
What is El Niño? The warming of the eastern tropical Pacific.
So, scientifically speaking, El Niño is basically the abnormal warm phase of a much larger climate pattern called the El Niño Southern Oscillation, or ENSO for short. And this isn't some yearly predictable event. It's an irregular natural cycle, popping up every 2 to 7 years. When it arrives, it completely alters the baseline conditions of the ocean and the atmosphere right above it, usually lasting anywhere from 12 to 18 months.
To really wrap your head around the scale of this, just think about the number 34. During a strong El Niño event, we're not just talking about a tiny temperature blip. The sheer influx of thermal energy actually makes sea levels along the equator in the eastern Pacific rise by up to 34 centimeters. And that's paired with a massive sea surface temperature spike of up to 5.4 degrees Celsius. It's just an immense, almost unimaginable injection of heat.
Section 2. The mechanics of the anomaly. Breaking the Walker's circulation.
So the crucial point here is understanding the normal baseline. Usually, you've got this system called the Walker circulation doing its thing. Trade winds are blowing steadily from east to west across the tropical Pacific. You can think of them like a giant broom, physically sweeping warm surface water over toward Asia and Australia. And that leaves room for cold, nutrient-rich water to well up from the deep ocean near South America. But during an El Niño, those trade winds weaken, or honestly, sometimes they reverse completely. Without that wind pushing west, all that warm surface water just naturally drifts right back east.
Let's actually visualize this with some incredible 3D mapping data. So this cross-section is from January 1997, showing our normal baseline conditions. I want you to notice the right side. That's over near South America. See that bright blue, cold water pushing upward? That is the nutrient-rich, deep water welling up toward the surface. It keeps the coastal waters cool and establishes a really steep boundary called a thermocline between the warm water on the left and the cold water on the right.
Now fast forward to November of that same year. Just look at how dramatically the ocean has changed. As those trade winds weaken, that massive layer of red, warm water begins sloshing eastward. And as it moves, it physically presses down on the cold water below. It's completely flattening out the thermocline. That boundary between warm and cold seawater is practically leveled out across the entire ocean basin.
Let's jump ahead to March 1998 and see how this builds into the climax of this sequence. By this point, we're looking at a full-blown El Niño event. Look at that massive accumulation of anomalous heat pressing right up against the Americas. The cold, upwelling water is completely suppressed. The ocean's surface layer is entirely dominated by this thick, warm pool. And because warm water evaporates so much faster, this acts like a massive engine, just pumping incredible amounts of moisture right into the air above it. Okay, here is one of the most astonishing facts I found in our source data. Because El Niño drastically shifts global wind speeds, it actually alters the total angular momentum of our atmosphere. Think of a twirling ice skater, right? When they extend their arms, they slow down to conserve momentum. Well, the Earth acts the exact same way. During El Niño, eastward winds around the globe speed up, meaning the atmosphere's angular momentum increases. To compensate for this, the solid Earth must actually slow its rotation. Yes, El Niño literally makes our days very slightly longer. It's a change so minuscule we only notice it using precision satellites, but conceptually, it is mind-blowing.
Section 3. Global weather disruptions. Drought here, deluge there.
We are really looking at a global climate seesaw here. On one side,
terrifying uncontrolled wildfires. Because the warm water and rain clouds shift east, places in the western Pacific, like Indonesia, eastern Australia, and New Guinea, get bone-dry conditions. That leads to severe droughts and massive fires. But on the flip side, you see an absolute deluge of rainfall. We're talking severe flooding in regions like equatorial Peru, southern California, and the Gulf Coast. Literally, drought here, deluge there.
It also completely rewires global storm tracks. We tend to see a sharp increase in tropical storms and hurricanes in the eastern Pacific, but simultaneously a decrease in hurricane activity over in the tropical Atlantic. And interestingly, it's not all devastation. These shifts can actually lead to reduced severe weather, like fewer tornadoes, over the interior U.S. in the spring. It also generally brings warmer winter temperatures across North America, which is highly beneficial for energy consumers trying to keep their heating costs down. It's an impartial reshuffling of global weather risk.
Moving on to Section 4, Farms, Fish, and Food. The biological toll. Let's start out in the ocean. When that warm water suppresses the cold, nutrient-rich upwelling off South America, marine life starves. The Peruvian anchoveta fishery is the world's largest fishery focused on a single species. In 2023, thanks to an intense El Niño, industrial landings of this one fish dropped by a staggering 50% compared to the previous year. And why does this matter to you? Because that catch is mostly ground up into fish meal and fish oil used for global aquaculture. A disruption there impacts farm-raised fish supplies worldwide.
And the marine damage isn't just happening off South America. Over in the Western Pacific, abnormal ocean currents leave behind not just warmer waters, but abnormally low tides. These shallow, incredibly hot conditions trigger devastating coral bleaching events. When corals are stressed by heat and shallow water, they expel the algae living in their tissues, turning completely white. This shatters the delicate balance of these fragile marine ecosystems, and recovery can often take years, assuming the reefs recover at all.
Back on land, shifting rainfall sparks widespread agricultural shocks. Weakened monsoons directly hit rice production in Southeast Asia and India. In fact, in 2023, these dry conditions prompted India, the world's largest rice exporter, to impose strict export bans just to protect its domestic supply. Meanwhile, water shortages heavily reduced the harvest of maize, a crucial staple crop in southern Africa. Across Latin America, decreased soil moisture damages both crop yields and livestock health.
Which brings us to our final section. Section 5, the humanitarian toll, society on the brink.
Now, what's really interesting about this is how perfectly these cascading consequences map out. Follow the chain reaction. Warmer oceans and shifted weather lead straight into droughts and floods. But from there, they trigger crop pests, food insecurity, and malnutrition. They ruin water supplies, causing infectious disease outbreaks. Ultimately, all of these impacts converge on massive health concerns and the forced displacement of incredibly vulnerable populations.
To ground this in the reality of human lives, let's look at the devastating 1982 to 1983 El Niño event. That specific anomaly was responsible for the loss of nearly 2,000 lives globally. Beyond that tragic loss, it caused the displacement of hundreds of thousands of people from their homes, driven out by a brutal combination of unyielding droughts, uncontrollable fires, and catastrophic floods spreading across multiple continents.
And these shockwaves even rattle our critical infrastructure. It goes way beyond just food and water. For example, severe water scarcity induced by El Niño profoundly impacts energy production. A key example from the data is the Simón Bolívar hydroelectric power plant in Venezuela. Twice in the last decade, abnormally low rainfall linked to this cycle lowered water levels so drastically that it forced nationwide power rationing. I mean, an ocean temperature change is literally turning off the lights in a country on the other side of the continent.
We've seen how today's dynamic prediction models spot an El Niño forming up to 6 months in advance. We know it's coming. So as we look to a future where climate models project even more frequent extreme events, I want to leave you with this question. How can humanity better adapt to these predictable but devastating cycles? From building robust disaster management capacity to rapidly adapting our agricultural practices, the solutions are out there. Thank you so much for joining me today on this explainer. Keep asking questions and keep learning.